Hi there! Today I'm going to be talking about the limit comparison test. So, the limit comparison test, we look at two series. So we have this series AN, and we also have series BN. And in this limit comparison test, it says that if the limit n goes to infinity for AN over BN gives a result C, and C is a finite number. And if C is greater than 0, then this basically proves that both AN and BN, okay, these series, behave the same. That is, if they both behave the same, then that means they either both diverge or both converge. So they either both diverge or both converge. So we are going to be looking at an example of the limit comparison test. Okay, so say we have an example that looks like this, and we are trying to find whether this series converges or diverges. So let's apply the limit comparison test to this to see as to whether it converges or diverges. So to do this, we normally look at the highest powers of n, okay? I mean, we look at the powers of n in this case, and we see that we have a square root of n here, okay? And then we have an n here, the numerator, okay? So we look at all our n's, and then we look at all the n's in our denominator. N, well, it's squared, that's going to be the highest power, so we're going to write that in. And then n, this is to the exponent of 1, so n here as well, so we're multiplying these, okay? So that right now what we're doing is we're trying to find another series to compare this series to. That's why we're using these powers of n. So if we were to simplify this, we see that this n can cancel with this n at the bottom, and then this is n, square root of n, so that's basically the same as saying n to the exponent of 1 over 2, and then this is n to the exponent of 2, so n to the exponent of 1 over 2 over n to the exponent of 2, well, we use our exponent laws, so we're going to subtract it, and we are now going to change this to a fraction, and then we are going to get 1 minus 4 is negative 3, and then the denominator is 2. Okay, so if we were to write this in the positive exponent, we would write 1 over n to the exponent of 3 over 2. And this is what we get. And so the series we can compare it to is this series. So I just put this right in here. So in this case, we can take this part as our AN. That is, this whole thing is basically the series with AN in it, and this whole thing is the series with BN in it, okay, this whole thing. However, this section right here is going to be our BN. That's how we can look at this. So let's use the limit comparison test to figure out as to whether this series converges or diverges. So we are going to do that, and the limit comparison test has AN over BN, right? Like this, and then we have to substitute in our AN. So our AN in this case is this whole expression. So we are going to write in our AN, which is right here, so we're going to rewrite that, substitute that whole thing right in here. then we have our bn, which is this. So we're going to rewrite that, which is the thing in the rectangle. So 1 over n to the exponent of 3 over 2. We're going to rewrite that in. And then we are going to change this division problem. Okay, we're going to write the division symbol. Because this long line, we're going to convert that into a division symbol. So we're going to do that. So it looks easier to work with. And then now we recognize that when we divide fractions, we have to flip the second fraction, so we're going to do that. So we're going to change it to multiplication and flip it. And then what we're going to do is we are going to multiply these terms in. So that way we can evaluate our limit. So square root of n is the same as n to the exponent of 1 over 2. This is n plus 3, so write n plus 3. And this is also times 3 over 2, so we're going to put this all in one fraction. So it looks better, and this is n plus 6 squared times n plus 5. And then we look at this and say, oh, n to the exponent of 1 over 2 and n to the exponent of 3 over 2, we can add these exponents together. So 1 over 2 plus 3 over 2 is 4 over 2. So n to the exponent of 4 over 2, and then times n plus 3. And then here, let's expand this. N plus 6 squared. We know that that would be n squared plus 12n plus 36 times n plus 5. Just like that. Then what we will do next is we will recognize that n to the exponent of 4 over 2, well, that's just going to be n squared. So we're going to rewrite this as n squared. This is n plus 3. And then let's distribute these terms in. So we can expand it. So let's do that. So n squared and n, it's going to be n cubed. N times 12n, that's just going to be 12n squared. N times 36, it's going to be 36n. 5 times n squared, that's going to be 5n squared. 5 times positive 12n, that's going to be 60n. And then 5 times 36, that's going to be 180. And then now what we do is we have to distribute the top two. So we're going to use the distributive property. So we're going to expand it. So n squared times n is n cubed. Squared times 3 is 3n squared. Its expression. And now we are going to evaluate the limit. So the highest degree term is n cubed, right? For top and bottom, so we're going to divide by n cubed. For top and bottom, so we're basically dividing all of these terms by n cubed. So if we were to continue this right here, we are going to divide. So n cubed divide by n cubed, right? This is for the top for this one. And then we have plus 3n squared divide by n cubed, and this is all over, and we have to divide all the bottom terms by n cubed. So divide by n cubed. This 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 divide by n cubed. And also 180 divided by n cubed. This is in the denominator as well, so this whole thing is the denominator. And as we can see, and this is the numerator as well, so it's going to be 1. This denominator is going to get really, really big, and this numerator is very small in comparison. This is n squared, this is n cubed, and n cubed is bigger. So this is going to go to 0. This term is going to go to 1 because n cubed over n cubed is basically 1. N squared and n cubed, well, n cubed is the greater one, so this is a bigger denominator compared to tiny little numerator, just like I said before here. So this is going to go to 0. And this as well, because n is smaller than n cubed, n squared is smaller than n cubed, and 60n is going to be smaller than n cubed, and 180 is smaller than n cubed. Okay, it's n to exponent of 0, but n cubed is bigger, n cubed is overpowering all these terms, but this is just going to be 1. So we are going to write this out. This is going to be 1. This is going to go to 0. It's going to go to 1. And all of these things are going to go to 0. So a bunch of zeros. It doesn't really matter how many zeros we write, but 1, 2, 3, 4, 5. You write 5 zeros, but still the same thing. You get the idea. So this will be 1 over 1 ultimately. And 1 over 1 is equal to 1. So what we got is, for our limit, is here. We got this. We got this limit to be equal to 1. And this is our c, right? So this is our c. C. C in this case is 1, and 1 is in fact greater than 0. So in this case, c is greater than 0, and 1 is a finite number. So that basically means that we can use a limit comparison test. And since we can use the limit comparison test, we can compare these two, the series, okay, and this series. And we're going to ultimately see if this series converges or diverges. Now let's look at this series that we compared it with. This series, we can see, is a P series. P series has a form that looks like this. In this case, P is equal to 3 over 2. P is equal to 3 over 2. Now, with P series, they're a special type of series, and they say that if P is greater than 1, then that means the P series converges. And if P is less than or equal to 1, then the P series diverges. In this case, 3 over 2 is greater than 1. So this P series, in this case, converges in this case. So since this series basically converges, this tells us that this series converges as well. And that is because we see in the limit comparison test, this is equal to 1, and when we compute these two together, and 1 is greater than 0 and is a finite number. So we can say that this series, therefore in the end, this series converges. So now I am going to show you another example with the limit comparison test. So here is another example. And we have to find out whether this series converges or diverges. So same trick as before, we're going to look at the highest powers of n. So the top, the numerator, we have n squared. In the denominator, we have n to the exponent of 6 with the square root. So we're going to include both the square root and the n to the exponent of 6. So we're going to make another series to compare with. And the best way to do that is find the highest powers of n from here. Now, we are going to simplify this. So we see we have n squared at the top. At the bottom, we have n to the exponent of 6. And this square root can be rewritten as a half, like that. And then we have n squared here, and then n to the exponent of 6. Well, we can use exponent law, so 6 times 1 over 2, just like that. Then we have n squared, and then 6 times 1 over 2. Okay, well, that's going to be n to the exponent of 3, and this will give us 1 over n. And then we can look at this as a series that looks something just like this. So we are going to compare this series with the given one, and we are going to apply the limit comparison test. So limit an over bn. So our an is this expression here, so we are going to rewrite that. Our bn is 1 over n, so we are going to write that, and then we are going to look at it and see the division sign. We're going to change this long division sign, fraction sign, into the actual division symbol. So we're going to write it like this. Then we recognize we can change it to a multiplication problem, just as we did before. And we will get n over 1. We flip the second fraction right when we change to multiplication. And then what we do next is we look at it and we multiply these n's together in the numerator. So we are going to get 3n squared times this n all over this, n to the exponent 6 plus 1, n squared times n was just to the exponent of 1, so we are just going to add these exponents according to exponent laws. Using exponent laws, we must add the exponents. 2 plus 1 is 3, so we get the 3 there. And then we have to look at these exponents of n and think, okay, well, what's the highest power of n? Well, it's going to be n to the exponent of 3, because, even for a denominator, this is also equal to n to the exponent of 3. That's because this square root, as mentioned before, is a half power. So it's going to become like this, like n to the exponent of 6 times 1 over 2, and that's going to be like the n to the exponent of 3. So it's the same highest power for the numerator and denominator. So we are going to divide by n to the exponent of 3 in the numerator and the denominator. So we're going to do that because that will help us with finding the limit. We are dividing by n to the exponent of 3. And then now what we do is we look at it and think, oh well, n613, n613, these will cancel out, and we will get 3 in the numerator, and in the denominator we have this expression right here that I have in the brackets. So we are going to look at this n613 and think of it as this. We're going to think of it as n to the exponent 3 squared with a square root. So n to the exponent of 3 squared with the square root, just like that. So it's kind of like the square root and the square will cancel out to get n to the exponent of 3. So it's like a fancy way of rewriting n to the exponent of 3. So we are going to continue. So we have 3 here in the numerator, and since we have a square root here, why we add the square root? So we can make this whole thing inside the square root, so it's easier for us to deal with. So now this whole thing can become inside the square root. N to to the exponent of 3 squared is also inside the square root. This part is also inside the square root, so combine the square root. We are allowed to do that. And now what we are going to do is we are going to recognize that n to the exponent of 6 plus 1. Okay, so we're going to recognize that n to the exponent of 3 squared is basically we just take 3 times 2, and that's going to give us n to the exponent of 6. So we're going to write n to the exponent of 6. And then here we are going to write that 3 over, and we see n to the exponent of 6 divided by n to the exponent of 6, 1 divided by n to the exponent of 6. So we're going to divide each one. And then we are going to get 3 over, well, this is going to be 1, right? Cancel out. So this is going to be 1. And then this part is going to be the only one with the exponent of 6 left, n to the exponent of 6. So we are going to, let's say, like, we're going to take this infinity and plug it in here kind of thing. Well, we're not actually plugging it in, but it's approaching infinity. So if this part approaches infinity, it just means so the denominator is going to get really large. It's going to get like really large, and it's compared to tiny little 1, tiny little 1, and big denominator. That just means that this is going to approach a very tiny number. 1 over n to the exponent of 6 is going to get really tiny, and it's going to approach 0. So we are going to get 3 over 1, square root of 1, plus 0, because 1 over n to the exponent of 6 approaches 0. And if we simplify this, we get 3 over square root of 1, which is just going to be 3. And hey, look, 3 is greater than 0 in this case. Since 3 is greater than 0, well, 3 is like our c in this case. So we were finding the limit of this, right? And we get c. Our c in this case is 3. And our c in this case is greater than 0. And by the limit comparison test, that basically means that the behavior for this series and this series that we're comparing it to has to be the same. Now, if we look at this series, we will recognize that this series is actually a p series. So we are going to write down that this is a p series. And remember, p series has a form that looks like this. In this case, our p is equal to 1. So this is to the exponent of 1. And it says that if p is equal to or less than 1, it means that the p series diverges. And since this series diverges, then that basically means that this original series also diverges, because in our limit comparison test, we got our result to be a finite number greater than 0. So we can write this, that this series, therefore, it diverges. Okay, so that is the end of the video. I hope this helped. Feel free to let me know in the comments down below what you think about this video and what you think about the limit comparison test. Anyways, have a great day, everyone. Thanks for watching. Bye!